Hello everyone, and welcome to the 17th Fault2SHA learning series. Today, I'm absolutely delighted to have Yann Klinger with us today, who will be talking on the Dead Sea Fault, a major plate boundary in Eastern Mediterranean. As most of you are familiar, the idea behind these learning series is to help us all understand different topics, different subjects, but also different regions where perhaps we might be less familiar if we don't directly study them ourselves. So I'm very pleased that Yann is going to help us today all learn a bit more about the Dead Sea Fault. And it's particularly in light of the recent earthquake in February that affected Turkey and Syria, and Yann will be saying a little bit about the connection with that in his talk. Yann is probably no stranger to a lot of you. I'm sure many of you have read his work and familiar with his talks. Yann, you have so many accolades to your name. I can't say them all now, but to note, you've been head of the Tectonics Lab at IPGP since 2013. You have many awards recently, the Pierre Prouvost Award from the French Geological Society, the Miller Professor at UC Berkeley, many consultancies and being on many advisory boards, editorial roles, over 9,500 citations and an H-index of 51. So a huge number of papers out there on earthquakes and faults, and with a number of them being on the Dead Sea Fault in particular. So we really are learning from the person who knows what they're talking about. So thank you, Yann, for joining us today. And he's very welcome for people to ask questions throughout. And if not, there's also should be some time at the end as well. So at this point, I hand over to Yann and just want to say thank you again for giving the talk today.
Thank you, Joanna, and thank you everyone to be here. So yeah, let's talk about the Dead Sea Fault, which is a major plate boundary in Eastern Mediterranean. And okay, I just need to move. Yes, okay. And so this fault is right here. It makes the connection, the boundary between the Arabic plate, which is moving northward, and the micro-Sinai plate here. It's a left lateral fault, and it's often tend to be forgotten in the big picture because it has been very, very quiet in the recent years. And so we don't think about it as a major structure so close from us, at least as Europeans. Sorry, I need to, okay, now it works. So indeed, the Dead Sea Fault, it's a major structure with a very simple geometry. So it's in fact a very nice strike-slip fault model. It has a well-constrained total offset of 105 kilometers. And you can see on this plot here that it has a very limited geometrical complexities, barely one big basin here for a pull-apart basin around the Dead Sea, and also a big compressional bend here at the Lebanese section that we're going to talk about a bit later. The main cumulative offset is well constrained from a major structure like the Palmyra to the east, which are connecting to those faults to the west, and also many very specific mineral veins and formation which are offset across the fault. So in terms of instrumental seismicity, as I was mentioning to start with, the Dead Sea Fault has been very, very quiet. You can see here most of the recent seismic activity, and on the left-hand side here, you can see that pretty much we have no earthquakes of decent magnitude. All those points here, you can see the magnitude chart are magnitude 4, magnitude 5, maybe sometimes, with the exception indeed of the 1995 earthquake that was a magnitude 7.3 in the Gulf Aqaba at the very southern end of the Dead Sea Fault. So pretty much no instrumental seismicity, which is not helping us to remember that this is an active structure. However, we have plenty of evidence for historical destruction with buildings like this Crusader castle along the Ateret pressure ridge here in northern Israel, where you can really see the wall, which has been offset left laterally by 2 earthquakes here. And also we have evidence for even older earthquakes, paleo earthquakes, like one nice example that probably many of you know are the seismites in the Dead Sea Basin, where we have those very nice convoluted beds, which are the signature of massive motion and local motion due to earthquakes in the Dead Sea Basin. So the Dead Sea Fault, as I just can summarize, has a very simple geometry, and we can understand the kinematic. We know the total offsets. We know it's hosting large earthquakes, and very important, it has a large population sitting around the Dead Sea Fault. We can count more than 8 million people living less than 100 kilometers from the Dead Sea Fault. So the Dead Sea Fault is in fact a very good target to better understand strike-slip fault in general. Today, I would like to talk more specifically about two things. First, the rate of deformation at multiple time scales, and then the way we accommodate the deformation through earthquakes along this Dead Sea Fault. So let's start our little trip by the instantaneous deformation. So instantaneous deformation is GPS. So what do we know about GPS here? In fact, with my colleagues and students and friends, we have been running GPS measurements across the southern section of the Dead Sea Fault. You have the Dead Sea Basin here for reference. You have the Gulf of Aqaba, the southern end of the Dead Sea Fault. And you have here all the points that straddle the fault. Those points have been surveyed 3 times, starting in 1999, 2005, and 2011 for the last survey. So not much to mention about the GPS processing. It was very standard, but just to say that it was really a challenge to succeed to do those GPS measurements across such a sensitive boundary here. And we are quite proud of our result, in fact. If we look at the results here, so this is the GPS vectors for those 3 surveys. The reference point here is the Ramo station on the western bank. You can see that all the points on the Sinai microplate are kind of 0, which is expected for this rigid microplate. And when you go eastward, away from the reference point, you see the vectors which are increasing as expected for some locked fault. And if we do a profile across all those points, this is what you have on the upper right section here, you can see that we have a very nice arc tangent, very typical from a locked seismic fault. And making a nice arc tangent fit here, we can determine a slip rate for the instant, let's say maybe 20 years, which would be 4.9 plus or minus 1.4 millimeter per year. So let's say 5 millimeter per year. We also see that we have a locking depth here, which is about 11 to 12 kilometers. So very standard for continental faults. If you look at the lower panel here, this is the fault, the displacement projected perpendicular to the fault. So across this, if we would have a shortening or extension, and you can see that on average, this is 0. So at least along this section, the Dead Sea Fault is really mostly, almost only a strike-slip fault. And again, slip rate here is about 5 millimeter per year from measurements 3 times over 12 years. So more recently, with some colleagues from Saudi Arabia, we were able to measure more points in the very end of the Dead Sea Fault along the Gulf Aqaba. So most of the points are in fact located on the eastern side of the Gulf Aqaba, on the Saudi side. And again, you can see that also we have only half of the motion here. Using the same kind of arc tangent modeling, we can again determine the slip rate for this section of the fault, which is in fact very, very similar to what we had northward, 4.9 plus or minus 0.8 millimeter per year. Maybe if we look a little bit more into the details, here we can in fact see from this second profile here that the locking depth seems to be a bit shallower in the south, suggesting that if we have earthquakes in the southern part of the Gulf of Aqaba, they might be a bit smaller in size, or maybe we have partial creeps. We'll come back to this at the very end of this talk. So one of the very interesting points of the Dead Sea Fault is that we have, in fact, the ability to do GPS measurements, so instant slip rate measurements, exactly along the same profile as where places we can measure slip rate over longer time scale, typically over the Holocene. So now I'm going to take you to one site, which is a very nice example of what can be done along the Dead Sea Fault here, where we have this blue diamond and where we have a nice observation for geomorphic offsets. And again, you can see this is exactly at the place where we already have a GPS profile. So we can do a direct comparison between geologic quaternary offset features and instant measurements here. Okay, so maybe you're not all familiar with the geomorphic analysis, so I'm going to take you step by step through this site. So now we are what we call the Wadi Araba. So we're looking eastward. In the far field, you can see the Jordanian plateau, which is standing about 600 meters above the Wadi Araba plain. And you see this huge alluvial fan here coming from the plateau, and which is opening along the valley. Right away, you can see that you have different colors, light colors for active streams, darker color for surfaces which are not anymore in reach for the river. And you can also note here that we have a sharp discontinuity. This sharp discontinuity, in fact, corresponds to the Dead Sea Fault itself. On the right-hand side, you have the same site. Now it's seen from above. This is a spot imagery, so pixel size is about 2.5 meters in that case. And again, you are very well aware of those active gullies here, which are entrenched into older terraces, darker terraces, I should say, which in fact are older and are out of reach from the river, meaning in fact, at this specific site, we have a little bit of uplift in addition to the strike slip. This is due to the small bend into the fault strike. What is interesting here also, and I would like you to note it, is that west of the fault, we also have some pieces of dark abandoned surfaces, and we're going to use those to estimate the offset along that piece of the fault. Last thing, on the right-hand side, down there, you have a little photo of those surfaces just to see how we have a nice pavement, which is very typical of surfaces which are abandoned, not active anymore, not reshaped by the current flow. So now we can start to map those surfaces. We have here these orange surfaces, which correspond to what we call F3, which is this abandoned terrace. And here we have a side view. We see now those abandoned surfaces, and we see the entrenched gully, like a C3 gully with this little patch of dark terrace on the western side of the fault. On the lower panel down there, you have a field view of the same place, where you can see the people for scale standing on F3, and you have we are now sitting inside C3 feeding channels. So we can continue our mapping. We have now this more recent terraces, F2, which is outside the feeder. In fact, we can see that we also have a little piece of this same terrace here inside this feeding channel. So the game here will be to say, okay, this guy here somehow had to be connected to that guy here. On the same picture, you also note that we have some other pieces of F2 in front of some other channels. So we'll be able to do reconstruction that should fit all those F2 pieces at once. So now we have a more complete map here. You have the field view where you recognize F3, F2, the abandoned most recent terrace, and F1 and the active channel right here, the fault being perpendicular to your screen right now. So if we look in detail at this satellite image, we recognize this piece of dark surface, which is outside the main feeder, and we can map it right here. And right away, we note some channels here, which are radial in shape, pointing to this submit here, what we call the apex of what looks like to be an alluvial fan. In fact, it's only half an alluvial fan, as the northern part here has been totally eroded by the channels continuing flowing across the fan. So we are only left here with this half fan, which was protected here by the upper terraces. So what we would like to do now is to estimate how much this fan has been offset compared to the feeding river. And to do this, we want to replace the apex of the fan in front of the center of the river. So this is what we have here. This is our best offset. This is 48 meters plus or minus 7, where we really put the apex of the fan, again, defined by those radial rivers in front of the center of this active channel. You note that when we do this, in fact, the edge of the fan here is matching very well with the edge of the little piece of inset terraces here. So we have good continuity, which is one more reason to believe that our match is meaningful. In fact, if we look at other places along the same scarp, we were looking at this one, but when we do this reconstruction, 48 meters, we also put this piece of alluvial fan, which is not so well preserved, in front of a feeder. So it shows that our reconstruction makes sense right here. Okay, so now we have the offset. What we would need is to know the age to be able to determine the slip rate over Holocene for this site. So again, some of you might be familiar. I'm not going into the detail, but here what we're using is exposition age from cosmogenic isotopes beryllium-10. So this isotope, beryllium isotope, is in fact due to bombardment by cosmic rays of quartz, mostly composed of oxygen and silicium. And so just to summarize a little bit, it's a little bit like you would like to know how long people have been standing on the beach. To do this, you look at their paint, their color, but you have to just assume that the longer they stay on the beach, the darker they are. This is almost true. Also, you have to think that they might also have come to the beach with some colors already. So you have inheritance. And also at some point, they start to be burned and they start to peel, and this is erosion. And so we have to take into account those different parameters to collect samples on the beach, on the terrace for us, and to determine how long they've been sitting there, how long people have been on the beach. So being okay with this, we can collect samples on those different terraces. In fact, we have two batches of samples, one on the F2 lower terrace here, and a couple of samples on the upper F3 terrace. On the left down part of the screen, you would see typical granite samples here that include some quartz into it. And so when we do all this chemistry and processing to measure the concentration of beryllium-10, this is what we get to the right-hand side. So you have the different samples distributed on the x-axis and the exposure edge on the y-axis. You can see that all our samples for the F2 terrace, the lower terrace, are quite consistent. They point to a general age of 12,000 years, which is the age of abundance of this terrace, while the ages for the samples which are sitting on F3 are much older, as expected, around 55,000 years. So again, using this age and the offset of 48 meters, we can derive the Holocene slip rate for this site, which is 4.6 plus or minus 2 millimeter per year since 12,000 years. So pretty much, again, about 5 millimeter per year. So indeed, the Dead Sea Fault is not super straight everywhere, as I mentioned, and mostly in Lebanon, we have this major bend where the fault is going from north-south to north, more like almost north 20, and bending back to a more north-south direction up north in Syria. So we have to decompose the deformation into two components, one strike slip and some, which is making some compression, which is responsible for, in fact, the mountains of Mount Lebanon. So we can try to know a bit more about this compressional part, which is sitting right here, that is probably sitting offshore right here. And to do this, we rely on some marine geophysics measurements, which are available. So on this, you have the topography. You can see very nicely the strike slip component along what we call the Yamune fault here. Very sharp, very easy to see in the topography. You have, in fact, a set of secondary strike slip fault here to the east. But you can also see offshore here a lot of structures, in fact, a lot of folds, which are affecting many of those canyons. And so from this nice bathymetric data, we can start to map offshore fault in front of Lebanon. And this is how we can, in fact, define the Mount Lebanon thrust, which is accommodating most of the shortening due to this bending of the strike slip fault system at the Lebanese latitude. Is this Mount Lebanon thrust active, and can we see sign of activity? In fact, yes. If you go along the Lebanese coast here and you look for evidence for uplift, in fact, you will see this kind of observation. This is uplifted bioconstructions. This is called vermitid, so it's kind of a local corals. And so those animals who are building colonies just at the fringe of the water get uplifted and then die. So when we collect samples all along the Lebanese coast here to try to date the death of this most recent colony, we find out that they all died around 551, which is the date of the largest earthquakes in the area, the major thrust earthquakes that generate a large tsunami in the Eastern Mediterranean area. So right now we have the source of these 551 AD earthquakes, which is linked to the Mount Lebanese thrust right here. So to summarize, we can put all the slip rates at different time scale along the Dead Sea Fault here. And we see that they are quite consistent, in fact, from the south, where we have a GPS rate, like the paper I was mentioning by Castro Perdomo here, 5 millimeters per year. We have along the Wadi Araba, GPS, but also geomorphology. We have trenching here. We have, again, trenching here. I'm going to talk a bit more. And then we have GPS and geomorphology to the north. So all those numbers are, in fact, pointing to a slip rate about 5 millimeters per year on the entire spectrum of timescales. We have only one point that we should keep in mind, in fact, which is a GPS point, which is to the northern part of the strike slip fault, which is pointing to 2.5 millimeters per year for the northern part, and this is an open question left. In fact, having this good consistency between geodetic and geologic slip rate for big strike slip fault is not so unusual, as you can see on the right-hand side, where we plot geologic rate versus geodetic rate for the big strike slip fault over the planet. And you can see that the Dead Sea Fault, but also many of the other faults, if we look at places which have the same kind of modeling and same kind of geometry, are very consistent between geology and geodesy. Okay, let's move to earthquakes. We have deformation. We know the deformation is about 5 millimeters per year. So now the question is, how do we accommodate this deformation? As I mentioned, we have, in fact, very few significant earthquakes. In fact, nothing really except the 1995 earthquakes. We also had a 1927 earthquakes, but it was a 6.25, so not a very large magnitude, which was about the Dead Sea Basin. However, we have a large corpus of historical events, and we know we have paleo earthquakes. So the idea is to build a spatial temporal earthquake catalog for this area. This is not so easy. How do we locate ancient earthquakes? I'll take one example. Here we are in Lebanon. Okay, Beirut is sitting right here. And we know we had a major earthquake in 1202, assumed magnitude 7.6, so really significant earthquakes. And in red here, you can see all the major macroseismic damage reported, including the site of Baalbek, which is in Lebanon, where there is a major temple and many of the columns collapsed there. You see that with this microseismic area, it's very hard to decide which fault was a causative fault for 1202. In fact, this area suffered a second earthquake in November 1759, again, magnitude 7.4, so quite significant. You can see on the left-hand side a keystone in Baalbek, again, which has moved. Also, it did not fall fully, so it's still standing. It's very impressive. And if you look at the area for the macroseismic data, again, very hard to decide which of the different faults was the causative fault for this major earthquake. So to try to answer this question, one way is, in fact, to go through paleoseismology. And for example, we did work on a site here, which is in the Lebanese mountain, close to the Bekaa Valley, which is this area here to the right. And we have this little kink in the Dead Sea Fault, you can see here, which is an extensional kink. So you can see on the upper right here, a nice little basin that was in fact full with a lake until 1930s, where it was drained. So we have lacustrine sediments, and this is crossed by the fault. So this is an ideal case for digging trenches right across the dry lake here. So if we open a trench here, you can see a few views of the trench walls. You see we have very nice lacustrine sediments, which means fine sediments, very well layered. In fact, you can also see that we have those dark layers, which suggest that the area is rich with organic material, so very prone to good dating. And on the right-hand side, you have just a little piece of the mosaic that shows you the beauty of this outcrop, where we have a lot of cumulative deformation, but also towards the top here, probably evidence for the most recent earthquakes along that site. So in this place, we had an exceptional sedimentary record and a lot of datable material. So for those of you who are not super familiar with paleoseismology, just a little do-it-yourself to know how it works. So pretty much we are at the bottom of a lake, we're piling up sediments, flat indeed, and then we break those sediments. So we disrupt the layers. And then because the lake doesn't care so much, we start again to put some sediments which are flat. And so we define the paleo-earthquakes event horizon, which is a virtual surface which separates to the bottom layers which have been affected by the earthquakes, and to the upper part, units which have not been affected by earthquakes, units that are post-dating earthquakes. And so if we can date those two units here, we can bracket the age of the earthquakes associated to the event horizon. Indeed, we can repeat this several times, and then we will define different earthquakes horizon. On the right-hand side, you have examples of those nice units, like this nice sandy unit, which is broken here, and we can map here and start to reconstruct the geometry of the cracks and geometry of the layers in that case. Okay, so for the Yamune Trench, for example, we were able to do all this mapping with all those different units here, very well defined, and also many cracks and faults that define up to 14 earthquakes in that case. So it's an exceptional record in that sense. But here I just want to mention about our most recent earthquakes. So the one which affected the top part here, which is called S1. And because we had a lot of material for C14 dating, we can really show here that we have no real rupture after 1270 here, which means definitely 1759 could not have ruptured this fault here. So we can say with certainty that along the Yamune fault, the very last rupture is a 1202 AD earthquake. So with this kind of reasoning on the Yamune fault, but also on the Sergeia fault and the Rashaya fault, on the Rum fault, we can really start to assign specific earthquakes to specific faults here, and we start to have a good scenario for earthquake rupture in this complex signal. So doing this, in fact, we can build a temporal catalog for earthquakes. This is not necessarily enough. We would like also to have more about displacement per earthquakes, because this is kind of critical if we want to talk about magnitude. And so to do this, I'm going to take you to a different site, which is slightly southward. So before we were somewhere here on the Bekaa Valley. Now we move southward. We're just north of the Sea of Galilee at a site called Beteja. And so this is in fact a floodplain from the Jordan River, which is coming from the north to the Sea of Galilee here. And so this floodplain is very flat as expected, but we had this small gully here that was flowing across the fault. So the idea here is, okay, we have a channel flowing across the fault. If the fault is moving, it should offset this channel. And if we dig trenches in this part, west of the fault, we should be able to find pieces of this old channel abandoned and buried down here. So this requires, in fact, 3D trenching. As you can see on the left side here, it's a lot of ground moving, as you can see. It took quite a lot of time and quite a lot of discussion with the local farmers as well, as you can imagine. And you also need to be very accurate on your positioning, because you need to be able to locate every single observation in this maze of trenches. At the end, you can see on the right-hand side the map view of all the trenches that were open over several years of trenching. The river, the channel was flowing from the right-hand side into the floodplain here, and we trench everywhere to really try to find evidence of this channel on the western side. Here is a view 3D of all the trenches. You can see that we can see some of those channels. In fact, they are not very obvious because those are fine material entrenched in fine background material. So we are in the floodplain, you have to remember, but still we could trace those channels and we could collect C14 dating material as well. At the end, we could do the reconstruction of several paleo channels. So you have here by colors, which are the dates, and just without even going to the details, what we can do is just reconstruct the geometry of those channels compared to their feeder, exactly like the alluvial fan before, but for buried channel. So for example, channel 2, we can show it has been offset by 3.3 meters, and we also have an age for the upper limit somewhere between 7th and 9th century. Channel 3 here has been offset 4.4 meters in 2 events, and we also know the age is sometime between 5th and 7th century current era. So now we start to have something very interesting. We have time here. This is just probability. So we have a time series. We see that we have 2 last earthquakes, well known in the literature, 1759 and 1202, and pretty much no other big earthquakes during this last 1,000 years. If we look earlier in time, the story is quite different. We have a series of earthquakes, which dates are quite well tight and in fact connected to historical earthquakes, but a flurry of earthquakes here, while only 2 earthquakes along that time section. So from this, we can start to build slip rates if we have displacement and time. And here it starts to be really interesting. So on this plot, on the lower panel, you have time and offset. Each small square is a specific earthquake. And you see that on average, over 2,000 years, we have a slip rate of 4.6 millimeters, which is very much like what we have anywhere along the fault, is 5 millimeters per year. However, this also should raise our attention, because if you subsample only this section, the first millennium before, after Christ, or if you subsample the last millennium here, you will end up with very different short-term slip rates. So again, here we have something we really need to take into account and keep in our mind when we do paleoseismology and try to derive slip rate only from paleoseismology trenching. We need to be aware that we need very long time record to average small variations. So this kind of work was done not only here, it was also done along the southern section of the Dead Sea Fault, where we have several other trenches. I'm not going into the detail here, just showing you one site as an example, the Qatar site. In the Qatar site, again, we have a very nice stratigraphy. We were able to determine the most recent event horizon. You can see here all the cracks are stopping below my E1 line. And so if we can date anything above it, we will get a bracket for these earthquakes. But in fact, we were able to determine 9/11 horizon here, which is quite a nice record as well. And again, here we were lucky enough that we had plenty of material for dating. So from there, we can build a nice age model. You have all the samples here. Again, mostly only C14s and very few rework dates. So this is very nice. And we can define time window for the different earthquakes for these 8 to 9 earthquakes, in fact. Again, what is very nice working in the Middle East is that in addition to this paleoseismological record, you have the historical record. And so you can really tie those time window for paleo earthquakes to earthquakes which are well recorded in the historical documents. And so now we know exactly at this specific trench that we have record for the 1458, the 1212, the 1068 earthquakes, and so on. So we can really start to work out the lateral extent of those earthquakes along the fault, and so start to build scenarios for rupture. So for example, for the southern part of the Dead Sea Fault, this is what we have now based on all our documentation and incorporating sites from other colleagues. We can really see how the different earthquakes are distributed further south along the Wadi Araba, or further north, or in the middle. And if we start to have the length, then we can start to loop and go to the magnitude. So this is where we're heading. We can now take all the data between the Gulf Aqaba and pretty much Lebanon, all the sites, our sites, Matthias Ferry's sites, Netas Wexler sites, putting all this together to build earthquake scenario and compare the loading to the release. So this is our earthquakes picture nowadays from paleoseismology and historical seismicity. So for each site, you have the possible correlation between sites, and so we can define different earthquakes. Again, you're probably very familiar with this kind of plot. So let's try to move on. Using this plot, we will go through scaling laws between rupture lengths and seismic slip, and we can try to estimate slip per event and then indeed magnitude. So first, the thing we have, so along the x-axis here, this is the distance along the fault, and along the y-axis here is the displacement. And this red line here represents the tectonic loading, so the amount of slip which has been accumulated due to plate tectonics along different sections of the fault, which are slightly different in time because this is depending on our record. So here we have 2000 years of record. Here it's slightly shorter. This is why it's a little bit lower, but it doesn't make a big difference. So this is what we have accumulated in terms of loading during those time window. Now, using our catalog of earthquakes, we can start to use our scaling law and say, for example, if we have major earthquakes along the Wadi Araba that would break the entire Wadi Araba, according to all the earthquakes we have recorded, we are able to accommodate that much deformation, which is shows in blue. Right away, you see that the blue line and the red line are not superimposed, meaning that, in fact, we already have some slip which is accumulated here and that we will need to take care of. Indeed, this is not the only option. For some of those earthquakes, we don't really know if those were one major earthquake or rather several small earthquakes breaking during a short time interval, like Izmit sequence in Turkey or even the most recent sequence here. So we have evidence for this kind of sequence along the Dead Sea Fault as well. If we do this kind of assumption, indeed, those earthquakes would be smaller, which means they would accommodate less slip, which means we would end up with a total slip accommodated by earthquakes that would be smaller, leaving a bigger difference between the loading and the part accommodated by earthquakes. The short summary of this is that whatever the scenario we like better, today we everywhere along the southern section of the Dead Sea Fault, we have about 2 meters of slips that need to be accommodated. And this is indeed at least a potential for a magnitude 7.3 anywhere between the Gulf of Aqaba and the Lebanese part, which is not really addressed in this plot. Okay, so to move on to more recent results, we also know that a lot is going on along the southern part of the Dead Sea Fault, along the Gulf of Aqaba, which is a place where the fault is in fact connecting to the Red Sea spreading center. So the difficulty in the Gulf of Aqaba, indeed, is that the Dead Sea Fault is underwater. But why is it so critical here? Maybe some of you know about this. Saudi Arabia is now building major infrastructure in this little corner here. They intend to build a full town. There is even projects to build a bridge here. So it's really critical to know what's going on in this section of the fault here along the Dead Sea Fault. In addition, the Gulf of Aqaba is that peculiar that this is the only place where we had a major earthquake during the instrumental period. So in 1995, we had the Aqaba earthquakes, also known as the Nueba earthquakes, magnitude 7.3. You can see surface rupture on the Saudi coast with like 25 centimeters of vertical offset here, still visible on the coast. A lot of aftershocks, probably complex multi-segmented ruptures, as we can guess from the body wave inversion. So until that earthquakes, we didn't know much about the structure of the Gulf of Aqaba. We knew it was some kind of succession of pull-apart basins with several segments here, but that was quite limited. So very recently, with our colleagues from Saudi Arabia and some student of mine, we in fact produced a new bathymetric map of the Gulf of Aqaba at higher resolution. Here you have a 10-meter posting bathymetry of the Gulf. And so this allowed to define exactly the current geometry at the bottom of the Gulf and to start to talk about segmentation and past earthquakes along this Gulf. So the 1995 earthquakes occurred somewhere in the center here, very likely involving several 2 or even maybe 3 segments in the middle part of the Gulf. In fact, if we look at the detail of this bathymetry, we can see a very sharp trace of the rupture, which is quite here, and many secondary traces which could have been partly activated during the 99. 1995 earthquakes. So the rupture is probably about 40 kilometers long with horizontal slip 2 to 4 meters. And in fact, Mathieu Ribot, my former student who was in the Gulf last week, sent me some photos. They have now new measurements, and it looks very promising in terms of imaging rupture. So one big question here is to know if we have potential for longer rupture in the southern section of the Gulf, knowing the big infrastructure which is currently being built at the southern entrance of the Gulf. So to try to answer this while we were doing the measurements for the bathymetry with Fault2SHA and some colleagues, we also collected many cores in the Gulf here, and this is ongoing work. So just show you some preliminary results. You see some of the core here, not very long because it's very sandy and very difficult to penetrate inside the bottom of the Gulf here, but we have example of turbidites in the core, so we can date and correlate the turbidite along in the Gulf here and try to discuss extent of earthquakes along the Gulf. And this is a little snapshot of the ongoing work, very soon finished. Indeed, we can recognize the 1995 earthquakes where it is expected. This is somehow our benchmark, but we can also recognize two series of turbidites that are consistent all the entire Gulf. 1068, which was well known as a major earthquakes affecting the entire Gulf, but also 1588, which was also known as a major earthquakes, even making some damage in Cairo so far as Egypt. So we have evidence here for Gulf-sized earthquakes time to time in the Gulf, and this is some concern again for this construction site, which is located at the Tiran Strait at the southern end of the Gulf. So I'll end here with a few more questions that should be of interest for future research. Like, how do we make exactly the connection between the Dead Sea Fault and the Red Sea system? Where is the triple junction, if there is any? How do we explain the discrepancy between slip rate in the north, those 2.5 millimeter per year, and the southern rate, which is 5 millimeter per year? Is it an earthquake cycle impact, or it's other reasons? And I leave it open. Also, we have ideas and we're working on this part of the question right now, but okay, stay tuned. I don't want to unveil the mystery so far. And what could be the largest earthquakes along the Dead Sea Fault? That's another quite important question, as we have so many people living around. We need to work on the hazard part of the Dead Sea Fault here. And just to finish, as Joanna said, I just want to make the connection between the Dead Sea Fault and what happened to the north in Turkey, because it's kind of related. So indeed, you are all aware of those two earthquakes that happened now about 3 weeks ago. And the southern end of the first shock, indeed, is very close to the branching with the Dead Sea Fault. In fact, the Antakya Basin and the Amik Lake here is at the connection between the Cyprus subduction here, the East Anatolian Fault to the north, and the Dead Sea Fault to the south. So such kind of large earthquakes on the East Anatolian Fault is a worry for what's going on at the northern Dead Sea. And we know here, this is just, I borrowed from Mustafa Megrawi's nice map, all the historical earthquakes in the area. We know we had historical earthquakes indeed along the East Anatolian Fault. We know we had earthquakes along the northern Dead Sea Fault. In fact, no major earthquakes for almost 1,000 years along the northern Dead Sea Fault. So this is a concern. And here we have now our two Turkish earthquakes, which are indeed loading this part of the fault. And just at the end, this is a very preliminary result calculation from USGS for a simple Coulomb stress map, where you can really see how the Dead Sea Fault here, its northern end at least, has been put into the red quadrant, meaning just bringing closer to the rupture threshold. Also, I'm not saying it's going to break tomorrow, but we need to be aware that the hazard has been increased for sure. And it's known from our colleagues in Lebanon, Israel, Jordan, that the microseismicity level has been higher those last weeks, and this is somehow a concern. So from this, I'll stop and I'll be very happy to take questions. Thank you.
Thank you so much, Yann. If anyone has questions, please do either just ask them directly or raise your hand, or if not, if you're unable to talk directly, write them in the chat and I can relay them to Yann. Yann, you were talking about the maximum possible earthquake in this area. Is there any reason to think it couldn't be as large as what we've seen recently along the East Anatolian Fault? Is there anything sort of preventing that?
There is nothing really preventing this, but probably the point is it could not start anywhere along the fault because, for example, the Dead Sea Basin is a major basin. It's quite wide. It's about 20, 25 kilometers wide. Indeed, there are cross faults. So you can always imagine a scenario where the rupture would use those cross faults to propagate. But if your earthquake would in fact start in the Dead Sea Basin, for example, and go bilateral, then you could really end up having a very large ruptures. This being said, no one so far in any paleoseismology site found evidence of such kind of earthquakes, and there are no evidence either in the historical record. But if they come every couple of thousand years, then they can be totally off the charts from this kind of record.
Thank you. Are there any other questions for Yann? Yes, Najib.
Hello, everybody. And thank you very much, Yann, for this very interesting talk. The historical seismicity of the Gulf of Aqaba, there was something enigmatic for me. In fact, nothing happened as far as we know between 1588 and the 21st of January 1983. Is this confirmed by your studies of turbidities or anything else? That no activity whatsoever is reported from the Gulf of Aqaba from the period of 1588 to 1983.
It is pretty much correct. We have evidence for something in the 19th century. You can see 1839 to the southern part of the Gulf. We also have, you see like a small turbidites here that we are not quite sure to connect to something. Same here, we have turbidites. We have no clear record to attach, but still they are here and they don't look like floods. But this is true that there are no record either in the historical document or in the turbidites for major earthquakes during this time period, which is a concern.
Unfortunately, I didn't listen to the answer because I didn't hear the answer, because about 20% of the letters are clear only, maybe because of problems of Zoom or etc. But we can discuss that later together. Thank you, Yann.
There's a question in the chat for you, Yann. Is there any creep evidence along the Dead Sea Fault?
So I would say the creep evidence. So let's grab just a map of the entire fault. That would be easier. Like okay, this one. So I would say the blunt answer is no. Okay, there is no place where we have obvious evidence for creep. This being said, we have, I was mentioning that the southern part of the, close to the Tyrant Strait here, the GPS measurements suggest that we might have a little bit of creep, but again, we have pretty much no data on the Egyptian coast, so it's hard to confirm. And there are also few places somewhere along the Lake Galilee here, Galilee Sea, where we have a dense GPS network from the Israelis that suggests that we have a very superficial creep. But this is not like the full fault is creeping. It's just the upper part, which is partly creeping. So Overall, we have no section with real creeps that would just account for the total loading.
Brilliant. Well, thank you very much. And thank you to the questions as well from people. And thank you to Yann and for everyone for attending. Really appreciate it. I've certainly learned a lot. So that was really brilliant. Thank you, Yann. We will be missing next month as it's Easter, but we'll be back again after that. So we'll be learning about different areas around the world. So thank you again, everyone, and see you soon. Bye.
Thank you.